Hello. I'm back reducing some dependencies. And where we left off, we were looking at memset, memcomp, and memcopy kind of stuff. And interestingly, memcopy is called by the default allocator in like the preload. And I think what's going to happen is at some point we will have a compiler intrinsic that copies memory without you having to rely on magical compiler optimizations to optimize away a procedure call and to deal with constant sizes and so forth. For now, though, we are just going to be slow. Okay. We used to use memcopy here, but we are removing dependencies. Okay. Default memcopy is going to do this. Why do we return something? That's dumb. I guess because original memcopy returned something. Okay, well. Do I have any dependencies that are written in this language? What do you mean, any dependencies that are written in this language? I don't understand the question. What are you calling a dependency? I mean, this is certainly a simple memcopy for sure. I don't know if I would call it particularly dank. Okay, well, let's make sure I didn't screw that up. Oh. Cannot subscription array whose elements are type void. That's true. That is true. Oh, we have another memcopy. Redeclaration. Why did he have a separate? That's weird, because that was in preload before, so that was unnecessary. It was just shadowing the preload. Does Sokoban run? Hey, look. It runs. And that's with our new memcopy. Our amazing high technology memcopy. All right. Memcomp, do we even use that? Probably we do. But I sort of feel like that's not a very common routine. Memset is a common routine. Who calls Memcomp? Wow, people call Memcomp. Oh, that's commented out. Okay. Well, we're going to have to do it, I guess. Is the compiler calling any smaller modules? Do you mean for the compiler to run or for your code to run? If you've been watching these streams, you see us dealing with external modules all the time. This whole modules folder that's full of all this stuff, like for years we've had that stuff in there. So I'm not sure what the question is really. Yep. The title of the stream is accurate. Okay, memset. We're going to make the value, we're going to try making it 8-bit, and we're not going to return something. That's bite me. Okay, so I'm going to do the same thing here. And then for something like that. See if anyone doesn't like that. It's possible that someone is trying to pass a signed variable and stuff, but this is our memset, not libc's, so we can say it's unsigned, and that's fine. Nobody apparently cared about that. Sokoban still runs with our new memset. Yep. I need to work on that movement code a little bit. All right. Will we eventually vectorize the memcopy? I don't know. I'm not sure that. So I don't really think vectorizing memcopy is that helpful. I'm not sure. I'm not up on the super latest things, but I believe, you know, instruction bandwidth is not the problem in that case. In fact, my current understanding is it's hard to do much better than the built-in copy instruction on x64. Like, you probably can't beat that without for the general case. Like, if you want to attack a very specific problem, like you know exactly the size or you know exactly the alignment ahead of time and stuff, then probably you can do better. But yeah, like for memset, like rep stas b is like about as fast as you're going to go. That might be a no longer accurate understanding, but that's what I heard. Why am I setting dest to underscore dest? It's because, okay, so a void pointer means you can pass a pointer of any type and you don't have to cast it. This isn't like C++. You don't have to cast it to void when you call this. So this is convenient because you can pass in any pointer type. But you can't subscript a void pointer. I mean, I guess we could assume the size is 1, but right now for consistency, you know, the size of void is 0. So we just say that's not really legal. So if you want to subscript this, you cast it to a type that has an actual non-zero size. So this is a 1 byte size, and then I can write bytes in there one at a time. That's all fine. You know, in a more elaborate memset or memcopy, I might write in 4 byte or 8 byte words at a time and so forth. Just for the compiler. The compiler is still all in C++. Okay, let's get rid of Memcomp. So we're going to do the same thing. Okay, Memcomp is weird because you're actually doing a subtraction, so it matters if these are signed or unsigned. What is it in C++? And do we care enough to provide the same thing? It's a void pointer. Note that this helpfully doesn't tell you if it's a signed compare or an unsigned compare, but that fucking matters because the result will be different. God, what terrible documentation. This is C++.com. Oh my God. How do people program like this? The sign of the difference between the first pair of bytes interpreted as unsigned char. Okay, this one actually specifies that. Oh, it said unsigned. Let's see. Okay, it doesn't say there, which, by the way, is where you want to know the information. Okay, there it says unsigned. All right. Not the best documentation, but the information is there. I kind of don't think these should be void pointers in that case. I kind of think that you should know that they're unsigned. That should be documented in the API. And so you're going to have to explicitly cast. I think that is more understandable. The understanding is worth more than the convenience. Okay. Oh. Let's do this. And we're using that it so many times, we might as well subscript it. And let's not give the optimizer so much, like why force it to realize things? So we'll just say Because otherwise you're forcing it to common sub-expression evaluate all of these, which is fine. It'll probably do that in an optimized build, but it probably won't do it in a debug build. And so this would be slower in a debug build, and we'd rather it not be slower in a debug build. So let's just do that. What does a C++ one return? Int. Okay, we can do that. Right, so if AI is greater, we return that, or else we return minus. Or we could cast these up to int first. I mean, we could return S8, honestly, because it can't. What does it mean to compare if you're not comparing unsigned chars? It's easy. You're comparing signed chars. They're signed 8-bit numbers. Saw a video recently how the libc memcopy slows down 5x on 32-bit builds because it decides not to use basic SIMD. I'm not sure I believe that. That's too big of a slowdown. But also, I mean, it depends on what it's doing when it decides not to use SIMD, right? If it's doing a naive byte copy that has lots of extra instructions in there, instead of saying like, you know, the x64 instruction, then, you know, etc. But I don't think, if you use this built-in x64 memory copy, I doubt that any SIMD version is going to be 5 times faster. I just don't believe that. Maybe I'm wrong. We'll see. No, you can't return AI minus BI because it's unsigned. I mean, I guess I can. Wait, can I just do the unsigned subtraction and cast to signed and return? Does that work? I guess that works. S8 doesn't seem right. If AI is 0 and BI is 255, that'll overflow. Yes, you're correct, actually. I don't know what I was thinking. You are correct. You are absolutely right. It's kind of a dumb function, like because you almost never really want this value. Like, the reason it works this way is so you can plug it into a sorting routine. But like, it's a bad idea just to sort on memory these days, because you want the result of your sort to not depend on your operating system or whatever, right? So Yeah, this is not really something that you probably should be calling. But I assume we do call it. Maybe not. Let's just see if anyone uses it right now. Yep. Serialized entity panel. All right. Well, let's see if we broke that at all. Not in any obvious way, but who frickin' knows? I can move things around. I can undo. So the basic serialization into the undo buffer is working. All right, great. Great. Guess what? That is all of the CRT dependencies in this file are gone, I think. Let's look at actually in module dot. So in the Windows, Linux, and OS X, there might be some. So let's look. libc exit, that's the only one, and we decided we're keeping that one for now. But so CRT in this file goes away. Why do we have libm? Those aren't here anyway. Memcomp. Oh, dude. Type mismatch. Wanted U8 given vector 3. Right. Well, that's just what I was saying about. Let's take void pointers for now. Just because, like I said, Memcomp is kind of dumb. So for providing it, let's be a little bit more C compatible, because that's the reason you would want it, is because you want to port code that's in C or something. So but we're still going to return S16, which is technically, S16 is size of int on a small number of architectures. So yeah. All right. Okay, well, let's look at CRT in Linux and Windows. How is that? Yeah. Oh, let's look in POSIX. Is there a POSIX? Yeah, I made that. There's no CRT. We have libc exit. Libc. Nano sleep. Shadur. Yeah. I'm going to let other people deal with that. We have an ongoing discussion about what's the best policy on like Linux. And what library these things are actually in and so forth. So I'm just going to concern myself with being CRT clean on Windows. All right, that is it. So we are doing pretty okay here. The only dependency for now is that libc exit. So we're going to check that in, and then I think my next step is going to be we could start looking for math routines, for example. So if I go to the math module, we're getting all this stuff from the C library. I'm sure someone is distributing a math library in C that doesn't depend on a C runtime. And that would be better for us to link anyway, because these things all change based on what operating system you're on and stuff, and there's no good reason for that. We would like that not to be true. Like, we want our cosign to behave the same everywhere. And so we'd rather link a known cosign. And of course, you can substitute a different math library if you want a different math library. So yeah. Anyway. So this is a big batch of our dependencies on the C library. Does anyone know you could return -1 and 1. Yeah, for sorting routine, you could return -1 and 1. But in theory, some sorting machines care about the magnitude. Some sorting routines care about the magnitude of the difference. And anyway, if you're going to be compatible, be compatible. Does return not jump out of the function? Yes, it does. Why? Did I do something wrong? This down here is for when you get to the end of the iteration and every byte was equal, right? That could happen. Somebody can call Memcomp on two things that are exactly the same. So you want to return 0 if that's the case. So the compile time here is fast, but my goal is to speed it up more than 10 times faster than it is right now. Like I've said this in a speech I gave a couple months ago. I think we can make it like 10 to 20 times faster than it is right now, compile speed wise. So that'll be good. But it's just not a priority, right? Our priority is to get it into a state where we can do the closed beta right now. And so it's fast enough for the closed beta. A lot of people tell you avoid multiple return statements. Do they tell you why you should avoid multiple return statements? Do they have a good reason? I'm going to heat up some tea and then we'll continue here. Can anyone tell me of a good math library? They say it can be confusing, like setting a variable and having to track what value that variable is by the time you get to the bottom of your routine isn't confusing. Like, seriously? Is anyone outside the company using the compiler? No, not yet. So I will go even further and I'll say that there's a very common pattern of that I do all the time, which is a procedure that sort of acts like a filter where you handle cases and return out of the procedure, right? And the further you go into the procedure, the more rare that case is because you handled earlier things by returning. Dude, I do that all the time. And once you know that pattern, it's very applicable to many things because the alternative is having nested if statements that are like 15 deep, which is ridiculous. You want to talk about hard to understand, try deeply nested if statements. Do multiple return values disable return value optimization? What do you mean by return value optimization? I think I've done a nested switch statement like once or twice in my very long programming career, and it was a bad idea both times. What do I mean by a good math library? I mean an implementation of these transcendentals, sine, cosine, tangent, and so forth. For reconfigurable computing, no. I just want someone's libm. I mean, I could search libm source, but I'd like something that is not necessarily associated with C, just because it might have a different historical provenance that would be interesting to look at. The Solaris libm. How are these? Are these done in Cordic or? This is like, the problem is this is going to be really old, but we'll leave that tab open. From the wiki link, return value optimization is supported on most compilers. But what do you mean by return value optimization is what I'm asking. When a function may return different named objects depending on the path of execution. That's just called inlining in the C and C++ world. And no, number of return values does not affect inlining. How about the DMath library? I don't know. I don't know anything about it. Let's take a look. D math library. Standard math. I'd have to translate it from D. Constants, classics, trigonometry, rounding, mod, floating point operations, introspection. Yeah, I mean, this is pretty much the set of things that we want. Let me see if they say where theirs is ported from. No, Walter just wrote it, I guess. Oh, cephus. Yeah, Bessel functions, 128-bit. Probability integrals. That's something I was thinking about for a different project. Learning about probability integrals. Dude, this is really not drag and drop right here. But we could probably do something with it. Some software may be from methods and programs for mathematical functions. It is copyright. What you see may be used freely, but it comes with no support or guarantee. Okay. Is cephus any good? This guy says cephus is better than the standard ones. Dude, beta integral, gamma integral, yeah, I'm not doing those today. Okay, whatever. You can use those in node.js. Okay, so that's one option. We can see on Stack Overflow if anyone espouses other options. Like, this is a thing where we also want to provide intrinsics, you know, so like, for example, there's a cosign instruction on the CPU, and you probably want to use that in many cases. So I think there's a cosign instruction. Is there? Am I making that up? Fsin cos, yeah. Right, so like, at some point we want to have intrinsics that say, hey, a call to cos can be substituted by this unless you disable that, and so forth. Just inline assembly of the transcendental functions. So the reason we don't necessarily do that is that, I don't know, there's maybe stuff that matters. Like, I don't know that fsin cos does the right thing with like subnormal numbers or some crap like that, right? So you want to provide a version that really does that. I don't know. I don't know, man. Yes, we're trying to get rid of all our libc dependencies, and this block of math routines probably is our single biggest dependency right now. Just by, you know, effort required to implement, I would say. We have a few other dependencies, but they're not big. And if you rely on people's libcs, then the behavior of your program changes for no reason as you go between different operating systems or even different, you know, different versions of Visual Studio on your machine. You don't want that. You want to know what your libc is. So eventually we will want these things implemented in our programming language. But before that time, we can at least have them be in C, but, you know, compiled in C such that they don't use the C runtime library, and then we can call out to them. And that'll be good enough for now, probably. Or, I don't know, if it's not a big volume of code, we could just straight up translate them. Oh, you had a good interview with Id. Right on. Was it in person? Did you, like, go to Dallas? Just phone interview? Okay, cool. CERN released their math library. Dude, CERN's math library is going to be too hardcore. Well, I'm glad the interview went well. Could probably look at the cephus sources there. Yeah, I mean, this page has all the sources. They're in these zip files, but let's see what that link is that you have. Oh, there it's, yeah. Okay. It's pretty good. Maybe I could just download it all here. Even like, you know, the hyperbolic cosine and sine, like I don't need that stuff right now. And whatever. Let's take a look at cosine. Cosine is going to be implemented in terms of something else, right? It's going to be, oh, is it sine cos? This is going to be, you know, look at that giant comment. Holy crap. That is not a very big file. You know what? Let's actually do this. Let's just get the math functions that we care about, and we'll translate them. And if that means I'm compiling more code sooner, then that just means, you know, like if this is thousands of lines, tens of thousands of lines even when it's done, that'll make the compilation slower, but then that's more motivation for me to speed it up, right? 8087. Oh my God. Oh, it doesn't give a full machine precision result. Let's do this. So what does this need? It looks like it doesn't really need anything except floor. Let's get floor. I mean, I hope this is free to use. Cephus Math Library. What's the license? It's copyright, but can I use it? Is my question. Torch Cephus. This is different. And a BSD licensed package. Well, I guess we'd have to get permission from the dude since he doesn't say a license. That's a little bit of a, I mean, I could do it for now and then hope we can get permission from the dude. I don't know. Do a quick speed comparison between C library and Cephus. I don't care about speed that much right now. Like if you want speed, use the CPU version, I think. You know what I'm saying? Well, I'm gonna start using this, and I'm gonna put a note that we need to get permission before we ship this. I guess. I don't know. I mean, oh, that's true. The other site said what you see here may be used freely. That is true. It's a good point. Okay. So let's get floor, right? Because that's one of our dependencies. I kind of don't want to spam us with that many files, honestly, but yeah. All right. Let's, so first of all, let's make this a multifile thing. We're gonna go all right, and then we're going to go there, and we're going to add that. Whoops, I put that in the wrong place. And I wrote the wrong contents to it now. Oh, jeez. What the hell is going on, Emacs? All right. So we've got two things here. Add. I kind of want to make this a capital M so that it sorts to the top, maybe, kind of like makefile. I don't know. Okay. Well, let's take a look. Like, these would not be a bad number of things just to pack into one file. You know what I'm saying? I don't know why they're in separate files. So, actually hook this up to the compiler more formally. So of course this wants to know if we're big endian or not. What the hell do these do? So deck has weird... No. This is going to be... I see. These are the same code. I'm starting to have less faith in this library a little bit. Okay. So we're going to delete the deck stuff. Def deck, if def, and if, and if. Dude, if def and C. Dude, look at this. It's frickin' K and RC. Holy free, holy. Dude, I'm not sure that I like what I'm seeing here, honestly. I mean, it's probably fine. It just, the way he did the if defs, I'm not sure about it. All right, now it's fine. Okay, 313 lines minus comment. How's that 12? I see. Wait, Emacs was using that Control L as a start of the count? That's so weird. I didn't know that. All right. Yeah, like calling it IBM PC, like you just care about this is just like endian concerns. And like, okay, let's get rid of the unknown stuff. And well, let's just translate the rest and it'll be more understandable by me in my brain after I've done that, and then we will see. Okay. So this is really just how it is for IEEE numbers. Okay, max num neg 0, we might need those probably. And cprot, yeah. Oh, are we calling these? Is nan? Yeah, okay, we're gonna need those as well, but that's fine. Okay. We don't need procedure prototypes. Whoops. It's not double. Okay. Okay, so we take the floor, and if the number went down, which it almost always will when you take the floor, unless it was exactly an integer, then we add one. Okay. So we're getting rid of seal and floor. So we're just going to cast up and cast back. That may not be the best thing to do, but that's fine. Kind of stupid, but whatever. Okay. This non-indentation of the code is kind of weird. I don't know, man. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So floor uses bmask. Let's put that. Well, doesn't matter. Bit clearing mask. Why have a comment explaining what the cryptic name bmask means when you can just call it the bit clearing mask? Okay. Oh, I'm not in C++ here. I don't know that I would do that way, but okay. All right, let's do this. Do those at the top, just get rid of it. Get rid of it. Okay. U.y is equal to x. Find the exponent power of 2. So what are we doing with this pointer afterward? We're setting something to 0. Either going forward or backward. This is something I could easily mess up, honestly. So we're going to have to test this. Find the power of 2. Yeah. Wait, what? This is not... Okay. Yeah, this is not how it should go. Like I just wrote this. So here, So, you know, if you've got a float 64, so you get the sine, exponent, mantissa, and so forth. He's not unbiasing the exponent here. I mean, we really should shift this first. I don't know. I don't totally trust that parenthesization. So we're doing that, and we're going to the other end of the number, and then he's going to zero out some things. Oh, minus OX3FF. That's 1023, right? Yeah. So he is biasing it. That's fine. We'll call it E. Oh my God, are you serious, dude? All right, if, else, if, right. Weird indentation, man. Different times. Okay. So if the exponent is less than 0, then this is a number that's less than 1, right? The magnitude is less than 1, right? So it's either, it's greater than or equal to, it's greater than -1 and it's less than 1, right? So if it's less than 0, the floor is going to be -1, right? Otherwise, the floor is going to be 0 because it's between 0 and 1. What? Dude, this is just what I would write. Like, I don't know why I'm getting someone's source code for this. Okay, anyway, so E is n bits -1 minus E. I don't understand this. Clean out 16 bits at a time. From the bottom of the number, while the exponent is greater than or equal to 16. So what? This is what? Okay, hold on. The exponent can be quite high, right? If the exponent is quite high, then he's just writing into uninitialized memory. Like, what? That can't be right if other people are using this math library. Does anyone on stream understand what's happening here? So it just doesn't appear to make sense. N bits minus 1, oh, right. So n bits, I assume, is like 64? Or no, 53. It's the number of mantissa bits. Right. Okay, so I don't like the reuse of E for that. Okay. So E is 52. So we're subtracting 1, I guess, for the implicit 1 bit in the mantissa. I don't frickin' know. So it can't be higher than 52. So we're going to loop at most 3 times and clear out 2 bytes each. So we're going to clear out at most 6 bytes. I don't understand why you don't do this a different way. This is kind of bananas, but okay. I mean, it's just not the way you would do it modernly. So again, maybe it's just that it's from a while ago. Like what I would do is I would synthesize a bit mask and the number, just kind of like he's doing down here, but just to the whole frickin' number. So let's make it work his way. So the thing is, if you do this with a bit mask, you don't even care what endian you are. There's also the muscle math library. Yeah, let's look. I'm going to make this floor and ceiling work. Let's see what their floor looks like, just so we can compare. libm. Well, I can't even find it from their page. Ah, someone put me a link right there. Okay. This definitely looks more concise, although they're kind of doing the same thing here. Okay, they're doing some trick here that I would need to think about. This like adding and subtracting 2int, where 2int is 1 over epsilon. I think they're just forcing rounding. And what does force eval do? This certainly looks more succinct to start with. This floor seems simpler, but actually by the time I get done with this one, it's probably about the same. Because we're about to delete all of this right here, at which point we just, and this. So like we really wouldn't have very much left. Yeah. Let's do. So this, if we were to, I was just being really pedantic when I wrote this version over here. You know, you can, as I was saying, you can do the shift. So 16, 32, 48, and then that 0 is 52. So you know, that looks a little better. But yeah, in general, when you do this as writing to memory, which you might do for very long floating point representations that don't fit in a register, that's when you have to care about endianness. But if you do it just as integer operations, you don't have to care about endianness. You know what I'm saying? Do I have a GitHub? No, I don't. Zig also has a floor. Whoa, that's a bigger floor, I guess. Oh no, the Zig floor is the muscle floor. It's the same one. That he just ported the muscle floor. That's exactly what that is. All right, well, you know what? Since we've been doing the cephus version, I'm just going to keep going and I'm going to make it my way instead of their way. And it's not really going to be the cephus floor at the end of that. Neither will it really be the muscle floor, which for all I know might be better. It might not. They're doing a rounding trick there that I would have to think about in the muscle one. How should I do this? I mean, we know it's less than 52, right? So we're just going to do this. This is kind of dumb, but we're going to pretend, we're going to do it just like we're playing Exapunks, and we're going to do it dumb to begin with and keep going. So we're just going to roll off the, we could do a mod here. In fact, mod 16 is of course easy, right? So yeah. Oh, I need to fix that. And then what's this? If x is less than 0 and u dot y is not equal to x. Yeah, that's just... x is less than 0. We'll look at that in a second. I need to understand what that does. Okay. But we said we're going to get rid of this union and all that stuff. So this is going to be relatively minimal. Okay, so instead of mask cursor, we're going to say mask that's unsigned 64, and then we're going to say and then we're going to say okay, and this, now that I deleted this u stuff, I don't remember, was that the integer version? Okay, that's the muscle one. So u dot y was, look at how long this was. U dot y was the float number, which we just checked the sign bit on. Yeah. Like once you go into integer, like just do integer. Wait, we haven't modified. We haven't modified u dot y at all at that point. Right, so this is just if x is less than 0. Yeah, forget it. We don't need the sign bit. We don't need the sign bit. Where did I put the, oh, I deleted it already. All right. Okay, we do this craziness. I would rather name this something else, but whatever. We do this mask. We're going to simplify this in a minute. We shift that, and then we say UF and equals mask. And then this thing, so the sign, whatever memory thing he did into the lower bits, the mantissa bits, won't change the sign, because the sign bit is the topmost bit of the thing. So bit clearing mask this is another mask. High mask is bit clearing mask E. Let's call that cast right? bmask. That seems right. So he's just clearing exponent bits selectively. I'd have to think about what that math does. But like, he's always leaving the sign bit set, except in the 0 case here, I guess. I mean, this is just, you know, ones minus the thing. I don't know why he's doing that on non-mantissa bits, however. Maybe it's not non-mantissa bits? Wait. Yeah, I don't know. I might be screwing this up. We'll see what happens. Okay, and then what is this down here? If x is less than 0 and u dot y is not equal to x. So the question is, how do we do this without casting back to float? Well, let's just say result is go back. UI minus equals 1. Result. And result. Is that going to work? I don't know. It certainly works with my brain better. And it's not operating on memory, and it doesn't care what endian we are. So we can get rid of all that. And in fact, we get rid of that. So what was this? LDX. What's LDX for? That's just a separate thing that was in this routine. So we don't need that for now. FRX. We don't need those. I don't even know what those do. Okay. So I feel like that rounding trick that Muscle is doing is maybe better, but maybe it's not. I don't know. This is just an interesting thing to learn and play about with. Okay, what's going to happen? Whoops. Well, the first thing that's going to happen is I'm going to accidentally rewrite this file that shouldn't be there anymore. There we go. It's not really the cephus one anymore, but oh, we don't have shift equals. I didn't do that operator. Do I have and equals? Yeah, maybe. Is nan and is inf. You know, I defined those in my thing, right? You know what? We're just going to go. Oh, this has some extra subtractions in it. We're just going to have this. So if the mantissa is 0, well, we might as well write isinf and isnan right now. So we do this, we get it as an integer. And we get the mantissa. Let's just copy my decompose. This is really not the cephus version anymore, if I'm being honest. But okay. Let's just get rid of this mantissa shift. Get rid of that. Oh shoot, this is not the raw mantissa. Because we're putting the implicit bit back. Let's not do that. Okay. That's the raw mantissa. Okay, so actually, let's is nan or inf because you sort of decompose it and look at both things at the same time, right? So unbiased exponent that's not right for 64-bit. Right. So the unbiased exponent is this thing. I don't remember what these numbers are. Right, it's we're going to have to rewrite this for 32-bit in a second. So it's basically, if the unbiased exponent is this number, right, 7FF is 1023, right? It has to be. Let's make sure about the order of operations there. Okay, so if the unbiased exponent is the maximum value of this fields, then, okay, well, the mantissa is that. Do we actually, our math, we might like define these fields. No, we don't define the mantissa fields and all that stuff. Okay, whatever. Okay, the raw mantissa is this. And if it's 0, then the sign bit is the top. If sign, return false, true. Oh, no, we don't need to know the sign bit. If the mantissa is 0, then it's infinite and not nan. Right? Otherwise, return true, false. Return false, false. Okay. So it's something like that, right? And then, okay, this is totally not cephus at all. So we're just going to put this outside this file. We're just defining this stuff so that we can use it. This is just me doing my thing. And we can just test these in isolation. Whoops, this is bool. So these are just like if you only care about one or the other. And I don't like these really short names, but that's what they're called in C, and I don't have a better idea right now, so whatever. Okay. I mean, I should just make this compile and then just test this in a test program, and then we'll test floor in a test program, and then we'll do the 32-bit versions of the same things. Is finite, right? If is inf x, return x. All right. Shift. Yeah. Neg 0. Well, right? 64 bits, sign bit set, no other bit set. Hex float. I think that's correct. Okay. Undeclared identifier. Oh, whoops. All right. Hey, it compiled. Let's go to our bug 118 that we're totally abusing the hell out of. And I'm going to say we'll keep our dead cells thing here active. All right, so we're going to say I hope we don't terminate on a divide by 0 right now. Okay, so do we have again, I don't know why I picked this random program, but it's what we did. Undeclared identifier, because we're not importing math. All right. Is inf A is true, B is false, C is true. How do we generate a nan? Like by doing an operation. So it says this is infinity. Let's do so false, true, false, true. What's a good way to generate a nan? Underscores works for decimal as well. It works for any numerical constant. You could change the first lines of ceil and floor to use your function if is nan or inf x, return x. Actually, that's not true. The function is misleadingly named because it returns, it doesn't tell you if it's nan or infinity. It gives you two. I'm just going to call it is nan is inf. Because the or is, yeah. You know what I'm saying. Are you thinking of this writer is finite not the same as is infinite? It said if it was not finite. So I deleted an exclamation point. If you mean in the cephus here, right? This used to say if not finite. Zero over 0 is nan. All right. E. Oh. I may not be calling. Oh, you know what? Did I make sure that I didn't? Okay, I guess we didn't have his nan before. This is how I convinced myself that we're doing the right thing. Division by 0. Oh, in the compiler. Oh, all right. Divided by b. The compiler won't tell us there. Let's see, catching division by 0 at compile time. Sometimes we're a little too smart for our own good. Oh, we didn't do e. All right. Okay, it's not inf. Okay, so now let's do the same for nan. It's the right isnan. No, true. Hey, there we go. Our isnan, isinf worked correctly the first time as far as we can tell. It's not that the compiler doesn't do constant folding. It's that it's a long story. I don't want to get into an argument about this right now, so I'm just going to ignore the comment. So is the 7FF valid or not? People were saying OX3FF is equal to 1023. Then the 1023 is probably wrong, right? It's the right answer is 7FF. The right answer is not. 1023 is the bias. So it's 2047. Wait. Yeah, something like that. Basically, yeah, that's what we're checking for, in fact. That's why it's better to check for this instead of a decimal constant anyway, because this is the pattern we're using up here. Anyway, let's do this for floats. So this is going to be float 32 infinity, 32, 32, 32. Okay. Same thing. We shouldn't. Oh, it's calling the float 64 versions. It's casting these up and calling them, which is why we're able to run. All right. I mean, I guess we could just do that. Like, yeah. All right, let's go back to our float convert. Our unbiased exponent is right shift 23. Is that OX1FF? What is 7F8 shifted right 3? Wait. It's just FF, right? Right, there's an 8-bit. There's 4, 5, 6, 8 bits, right? So if the unbiased exponent is 255, then the raw mantissa is this. Yeah. Something like that. Doesn't that cast S32 have to be S16? No. The cast here is not truncating the number because we're masking the bottom bits. All this is really doing is saying, you know, for up here we were like, don't make it 64 bits because it might be faster just to have a 32-bit number. That's really all that cast is doing. Probably doesn't matter, and probably we should have a way to say cast to whatever is a fast number. It probably shouldn't be cast S32. Okay, so that's a potential compiler feature. So here, the cast S32 is doing the same thing, but it already was U32. So like, you know, you might as well just, yeah. Okay. So let's make sure, and then 64-bit is inf and 64-bit is nan. Whoops, I got to run the test program, not Sokoban. Okay, so we're calling the 64-bit versions, and then we're calling the 32-bit versions. True, false, 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 true. Right answers in both cases. Great, ship it. We didn't even have those yesterday. Now we have them. What are you doing? Okay. Someone decided that we should go to libc for integer absolute value, which, no, we're not going to do that. We're not going to do that. Why? Why? See, this is, you might think, oh, the C version does something fast, but by the time you call into a frickin' DLL, that's not fast. This might get optimized into something. There's no way this is getting optimized into anything. Like, it's just no. No. Okay. So we've got our isnan, our isinf. That's all great. We still haven't replaced these. Well, we did replace floor and seal, so we get to test that next. Well, numbers. We don't have float 32 floor and seal yet. And I don't know. Yeah, we probably should make them. 0, 1, 1.1, 3.33333. Well, that's too many digits for float 32. Whatever. Minus and infinity. All right. So floor whatever equals whatever. Let's make this a fractional. It floor it, and then let's put the floor and the seal at the same time. Okay. Semicolon. Division by 0. Okay, we won't put that one. All right. Yeah, it's totally broken. I screwed it up. Not as badly as one might think, but I did screw it up. And it's in the final bit masking part, I think, which is the part that I don't totally understand. So it's not surprising that I messed it up. So like if I do negative numbers that are smaller, those should probably work. So I feel like, oh, seal and floor are giving the same value there? What? Well, let's make sure we're calling our right ones before we do anything. Okay, well, yeah. All right, great. It's weird to me that seal and floor, I don't think this is correct. I think we're actually printing this wrong. We're going to have to investigate that separately. But, you know, this is obviously woefully wrong here. Heard that for floats, you can test all possible inputs in 5 minutes. That's approximately true, yes. I know I can use isnan, isninf on the first line, except that I still have to check both return values. Who cares? Who cares? That's not important. What's important is that this is wrong. It is wrong. So we only should ever be using the top 5 because remember, it was 52 minus or whatever, n bits minus 1, right? So 52 minus E. Oh, wait. Right, where E is known to be greater than or equal to 0 to start with. So we're less than or equal to 52. Which means we can only ever use the first 4 elements of this frickin' array anyway. Which makes sense because otherwise we're into the exponent. Right? Like we should never... We should never see that be bigger than like 3. Oh my God. Why is it 15? Oh, because it could be, right, it could be like 31. And so you subtract the first 16 and then it's an, okay, so what I said was wrong. What I said was wrong. I just don't understand what this code is doing. So the thing is, this is powers of 2 off of this. And the only way that happened was by me screwing with the exponent bits, which I shouldn't be doing. Oh, right. Okay, so what we really should do, okay. What we really should do is just do this. Just go straight for the gold, because this mid step that we did are just confusing us anyway. So we're going to say E mod 16 is E and, well, 16 is OX10, so it's OXF, right? And E div 16 is E4, right? So that's fine. And then so we're going to say mask is bit clearing mask of E mod 16. All right. And then mask is mask left shift E div 16 times 16. Except we need this. So we put that bit clearing mask in the low bits, and then we shift it left by the number of 16s. I mean, this is stupid. This bit clearing mask is just the same. I could just shift by the number. Why am I doing 16s? This is dumb. We're going to just make it work. And then we'll get, because this is just shifting by the number of bits. That's all it is. All right. Let's just make it work. Let's just make it work. All right. No, not that. Oh. Redeclaration of mask. Wait, what? Oh. Type mismatch. Oh, it doesn't like the S64 with the U16. Whatever, we'll be more specific about it. Hey, look, it worked. Aren't we special? Even this worked. Okay. See, sometimes you don't do it the wussy way, you just do it the real way. What is the reasoning behind doing all this in a library and not just emitting a floor instruction? Because what if you're on a CPU that doesn't have a floor instruction, right? Or what if you want special behavior in your floor instruction? What if someone wants to copy this and so forth? I agree that in reality, we probably want a floor instruction. In fact, for all this stuff, I'm just sort of doing this as an educational experience right now. In reality, it is quite possible that what we really want in the near term is to just generate the instructions. And so maybe the thing that I will do after this, because remember the whole goal here was the whole goal is to get rid of these dependencies. I don't think there are instructions for all of these, so we certainly need functions for some of them. I don't think there are arc functions on the CPU, but certainly for cosine, sine, tangent, and floor and stuff, yeah, there are instructions for that. And we could, instead of actually writing code here, we could just say, look, we use a CPU intrinsic for this. We know every CPU we're going to target has this, so we don't even bother making a function for it. That would be fine, unless you wanted very pedantic float behavior, in which case maybe you just link a different library anyway. I don't know. That might be the best thing for those functions, but certainly for many of these, like log, there isn't a log on the CPU, is there? Anyway, but also this is just fun. It's like I'm playing a Zachtronics game here, man, right? We're going to have, this isn't going to be the cephus floor like at all by the time that we're done. We started with it. We're not going to end with it. Okay. Find the exponent, right? So well, so this bit clearing mask is just all ones left shifted by whatever. So instead of doing this div 16 and mod 16, we just say mask equals mask left shift E, right? I believe that's the same thing. That could be wrong. It's not quite right. Weird. Okay, what did I do wrong? 0, 1, 2, 3. Yeah, it's just that many 0 bits on the bottom, right? Well, let's do this one step at a time. What if we do this? Because I might have just screwed up something really dumb. So let's say mask is all Fs. And then we're going to say, as this step, right, that should be the same thing. Let's make sure that's the same thing. Nope, totally screwed it up. See how easy it is to screw things up? Why did I screw that up? FF80, FF. Why is it? Oh, because I'm ampersanding by the bit clear. Duh. Okay, yeah. That was obviously a mistake. All right, so we just left shift by emod 16, and that is correct. We're getting the right answer. We're getting the right bits and all that. Okay. And then we're left shifting by e div 16 times 16. Did I just screw up something really basic? Like that should be, okay, it works now. I must have just done something really dumb. Yeah. So we get rid of this. We get rid of these. We don't clear out 16 bits at a time. We're getting pretty, oh, we get rid of bit clearing mask. So we have no memory accesses. instead of n bits, we're going to say mantissa bits. Oh, right. I know why this works now, because 2 to the 0 equals 1, and floor is masking out anything less than 1. So you just want to 0 anything less than 2 to the 0. I get it. It's very simple. I could have written this from scratch if I thought of that. Yes, it's easy. You do it all day. What specifically do you do all day? The floor intrinsic generates variants of the round SS instruction, which exists as of SSE 4.1. You can typically check extensions available for... Yeah. Right. Anyway, this was good times. So here's my moral dilemma. Like, we started with the cephus code, but this is not the cephus code at all anymore. So do I say this is mine now, or do I put a blindfold on next week and work it out from scratch and write it from scratch? Because, like, I'm pretty happy with this. It's pretty reasonable. I guess this part is still cephus right here. And this part, but like that's just the spec of the function. Anyway. Yeah. Floor was very heavily modified. It's not the same code. It doesn't even work the same basic way anymore, but I did use the cephus routine as a starting point for the modifications. Anyway. Like, it'll be kind of interesting. I'm not going to do this tonight, but to like remember and learn how sine and cosine are computed and all that. It's probably just lookup tables, but maybe not. It's probably just linear interpolation in lookup tables. So we're not really doing float 32 versions of these, but I mean, maybe you just let it cast to the float 64s. Yeah. I mean, I'm fine with that. We obviously could, so the same way that I did the float 32 versions with the different numbers for the mantissa size and all that, you could transcribe this to float 32 directly. You know. Yeah, the reason the cephus one worked differently is just that that was probably the fast way to do it for computers back at that time. But today, this is the faster and cleaner way to do it. Is, you know. And even instead of doing this bitwise and, it might be faster just to like right shift and then left shift the number to mask off the bits, because that way you don't need it constant in memory. The thing is, variable length shifts on x64 are actually expensive. It's ridiculous. You would think that that's a cheap, at least last I checked, they might have changed it on newer CPUs, but like a shift by a constant amount is very cheap, but a shift by a variable amount is actually a relatively expensive instruction. So doing that twice is probably not that great. Handmade Hero had an episode with a special guest a while back on sine, cosine, and other flow stuff. Maybe that was Fabian. I don't know. Chebyshev sine approximation is apparently how some scientific libraries compute sine, cosine. Code on the side is also quite succinct. Okay. I'll read up on that. Couldn't you do the floor with a simple cast correcting if negative? I don't think so. The reason is that your number could be some large-ish integer times 2 to the 24, right? Or sorry, times 2 to the 1023, positive 1023, right? And so if you try to cast that to a 64-bit int, 2 to the 1023 is a lot bigger than 2 to the 64, so you're just going to run out of bits. You're going to not be able to cast that to integer. You could check if your number's that big, because of course, if it's that big, then floor shouldn't do anything to it because it's a large integer, right? So it's possible that might be a better way to do it on a modern CPU. I don't know. Let me make a note about that. Someone in chat asked whether we should just implement floor by casting to int. Obviously we and back. Obviously we would need to check the exponent and return x if it's too hot to fit. This might be simpler than this implementation, but it's still more of a hack than just using range index. So maybe we should just get our intrinsics figured out. Someone's saying OX, lots of Fs, shouldn't really be a constant in memory. Hopefully it can be generated with one instruction. If you look at what x64 compilers do for large constants like that, they often stored in memory. I guess you could, right? You could do, like XOR RAX, and then sub RAX1, RAX. You could do that. Maybe a compiler would be smart enough to do that. Maybe not. We're not smart enough to do that, but our x64 backend doesn't optimize at all. Yeah, convert SS to, yeah, how is casting from Florida into itself implemented? Yeah, we use the SSE instruction on x64. I think you can just move it directly on x86. It can sign extend from 254. That's true. A sign extended move from an 8-bit constant, right? So you could do is it, how do you say this in assembly? Is it just A if it's 8-bit, or AL, right? So you would say move AL 255 and then move it. I don't remember exactly what it's called, but you know. Something like that is what you're saying, and yes, that would work too. Whatever the syntax is for that. Move SX, yeah. Yes, and that would also be a better way than generating that bit pattern. When it comes to stuff, I've definitely seen, so Visual Studio, when you manipulate floating point numbers, they tend to have float constants in memory like that. I guess maybe because they're not that easy to generate. But even stuff like negating a floating point number, Visual Studio generates code that has a 64-bit number with just the sign bit set, a 64-bit integer, and it like XORs it. That's how you negate a floating point number, according to Visual Studio. That might be the fastest way to do it. I don't know. Let's do questions, because I feel like we've done a good day's work, except that I've totally mangled this file. Let's run our tests. Sokoban runs. All right. Let's not check in our bug 118. Yeah. What do we implement? Mem copy, memcomp, and memset to remove libc dependencies. Remove dependencies for integer abs. Boom. That's a good evening's special streaming work. What are the current dependencies? I don't even know exactly. We're just going through and finding the ones. The big ones that we were looking at today were all these math routines. Like all of these are coming out of the C library right now. And so the reason we did floor and seal was because those were like being used in Cosign or something. But it is an interesting point that maybe I should just implement intrinsics anyway. Like that could be a fun weekend compiler stream. Like I said, we don't have intrinsics for all of these, but I mean, a lot of these, like tangent is sine divided by cosine, right? So we can have an intrinsic for that. Atan2, I don't know. But you know, we can just do some of these. And rather than having the compiler magically substitute for a function, we just say, we say this is an intrinsic called cos64, right? And then, maybe we have ways to forbid code from using specific intrinsics or whatnot. You know what I'm saying? And then we could get rid of many of these. I like that. I like that because, we're going to need intrinsics for SIMD operations later. So like, why not start now? If you dig it. Dependency Walker could show your dependencies on Windows. It can show them for any one given output program, yes. But we kind of care about all the potential dependencies that anyone could get from compiling anything. There's an A10-2 instruction. Wow, okay. And A10 can just be A10-2 with one. There's probably an A10 instruction. Yeah, so let's just do intrinsics for these because we need to do those eventually. And I haven't done any x64 stuff in a real long time. So, yeah. Yeah. At which point we're going to delete that version of Floor that I just wrote, or maybe put it in archival code somewhere. Yeah, the more I think about it, the more I like that idea of just starting an intrinsics stream and just doing it. If you implement intrinsics, does it make it easier to also implement inline assembly, or are they unrelated? I would say they're unrelated. Or they're super loosely related, but they're not going to overlap at all. They're not going to overlap. I say that now. I don't actually know. Okay. Questions? I'm going to grab a quick snack, but send questions to me and we can talk about it. Any questions? Implement inline assembly as a collection of intrinsic. I don't know if that's meaningful. Any questions? Or are we just chilling on a Tuesday night? Why are we using SVN? Well, if I had a FAQ on this page, it would tell you, but I don't. And I answer that too much, so I'm not gonna. Sorry. I don't like this wheatgrass flavored aloe drink. I like the regular flavor. Y'all hear about how quantum computing is kind of obsolescent now? I don't know what you mean there. Is there a way to address a second return value from a function without a local variable? Not currently, no. Not currently. It could be intrinsics for OpenMP. Maybe. I'm not a big OpenMP fan, but I don't know. 18-year-old Yuan Tang has proven that classical computers can solve the recommendation problem nearly as fast as quantum computers. This result eliminates one of the best examples. I don't know what the recommendation problem is, but I mean, Shor's algorithm is the best example of a quantum algorithm being faster, right? So, and I don't know what nearly as fast means. I would read Scott Aronson's blog to see what he has to say about this. Well, if Scott Aronson supervised his thesis project, it's probably good. Yeah, a polynomial of degree 33. I mean, that's polynomial time, but you know, it's potentially large. But as he says, probably in practice it runs faster than you can prove it to run. Have I implemented memcopy by loop unrolling or rep moveS instruction? Neither. Right now it's a loop. But that is another thing we could use an intrinsic for if we have an intrinsics. Yeah. Well, so Grover's algorithm isn't really a classical algorithm in any way. Like, it doesn't have a classical equivalent, right? I mean, you could formulate the same problem classically, but you wouldn't. Do I care about sum types? No, I don't. How do we do error handling with return values? Have I seen the draft proposals for improving error handling in Go 2.0? I heard that there were draft proposals for Go 2.0 out, but I have not looked at them. Did I solve the notebook dilemma? Yeah, I ordered a Lenovo P1 and we're going to see how it is. I worry that the GPU isn't very fast. And also, they probably won't ship it for like at least a month, but we'll see how it is when they do. Any advice for beginner game developers? Yes. Stop asking for advice and start making games. If Emacs was fast and wouldn't hang, would I recommend it for everyone? No, because the configuration being in eLisp is just bananas. And in the year 2018, I don't think anyone should have to deal with eLisp. Do I do micro optimizations often? Not too often. But when they matter and when I get to that point in development, then absolutely. Do I care about ADA-like refinement types, post precondition range bounds, and other correctness guarantees in the type system? Well, I would say I don't have very much experience with using those in actual programs. And since we have enough work to do right now, I am limiting my design to be about doing a good job with the things that I know and understand to be applicable to the work that I want to do. After we get this first version of the language out, we could take a look at stuff like that. What happened to the March closed beta? I don't think there ever was a March closed beta. We've been pushing back the closed beta date because stuff isn't totally ready. We're gonna close beta when it's ready. How do you promote your games before, during release? It's different for every game. I don't know. I can't tell you how we're going to promote our next game because we just have to make that decision when the time comes, and conditions change so quickly that it's not worth thinking about it yet. It's just a waste of time. Because if we come up with some plan now, that plan will be obsolete by the time we're ready to release the game. Do default values for proc parameters have to constant, or do you recompute on every call? So right now they have to be constant, but there is not really a technical reason for that. We could allow them to be non-constant. I just don't, because, you know, again, just trying to keep the complexity of what we have to think about down. But that was suggested actually by one of the people in the company. One of our small user base was like, hey, I would like it if I could have non-constant default values to procedures. And so it's potentially on the table for future situations. It's just I don't want to do it yet. Some games need a lot of complex UI. I usually write this with reactive libraries, but that works only with a lot of lambdas and capturing. What approach should I use here for that task? I don't know what a reactive library is. That sounds very Hacker Newsy to me, and I associate Hacker Newsy with bad. A lot of lambdas and capturing doesn't sound like a good way to do a UI to me. I would use an ImGUI approach, an immediate mode GUI. That's what I do. That's what I have done for decades. It works great every time. And that's how the game that we're going to give as a sample code will render its UI as well. What was the current state of iterators? The current state of iterators is they will be re-implemented a different way when a new feature happens, and that feature will be the next feature after libraries are done. And I'm working on library or modules just to disambiguate between C++ libraries and whatever. After modules are done, and I'm working on the module improvements now. So it'll get there eventually. What's been going on is I spent a fair chunk of time working on the game and not very much on the compiler, but now I'm shifting my time back to the compiler for a bit. What happens if you defer a free and then return the freed pointer? Then you return a pointer to freed memory. Well, Acer has a powerful notebook, but it has separated trackpad and it's really big. Predator 21. Oh yeah, I saw that. Yeah, that's a little too big for my purposes and scary in other ways. What's the situation with concurrency, and will there be Go-like channels and coroutines? No, I don't really believe in the Go philosophy about parallelism. And in fact, I think concurrency, the way Rob Pike uses it, is kind of a weasel word anyway. So, like, real parallelism is hard to make fast, and all of these high-level abstractions don't really help you do that. So, our situation with helping parallelism is going to be other kinds of compiler features that help you make correct code and have more confidence that it's correct. It's not going to be And then aside from that, you'll just be using regular like mutexes or lock-free algorithms or something, right? We're not going to dictate, that stuff. How does the system library thing work? Does the compile? That sounds like an incomplete question. Since I work at a place that uses a terrible chat program and even worse issue tracking system, I'm wondering how your team communicates. I don't know, like some of the people are on Slack all day. I feel like that's a waste of time. I don't do anything like that. I just either talk to people face to face or I email people. In a previous talk, you mentioned wanting to find more simple yet powerful conventions like temporary storage. Since then, have you found any others? Not yet, but we haven't done too much thinking about that. The main convention that I want to try to figure out is a way for libraries to coordinate without explicitly drawing dependencies on each other, right? So, if I have a library that draws fonts, then maybe it wants to draw them with OpenGL and maybe with Direct3D, and that depends on what graphics API you're using. And like, is there a way that we can make it easy for the program to tell the libraries and the libraries to tell each other which of those is going on? And that's a general enough mechanism that it's not just about that specific case of like a specific rendering API, but that works for a lot of things. I don't know. That's what's been on my mind today. I don't know the answer for it yet. How do programs run on multiple versions of Windows if the syscalls change? They call into a DLL. Yeah, I mean, the Windows API is mostly in kernel32.dll. So I assume if the syscalls change, then a different kernel32.dll is shipped on that machine, mapping the API to the new system calls. Something like that. How do I feel about scripting languages such as Lua and how they can be used in game development? I don't really think there's much of a place for those like Lua today. It sort of made sense 15 years ago or something, but not today. Not today. All right, everybody. I think that's been a stream. Let's find someone who's programming. Let's find someone who's programming. Wait, but you link against kernel32 lib, right? Isn't the point of the lib that the code gets included in your executable, therefore not calling a DLL? You would think that, but no. So some .libs are actually static libraries that link the code into your program. Some .libs are stubs for DLLs that just say, to get the implementation of function X, call into DLLY. That's what kernel32.lib is. It just says, look in kernel32.dll to find the definitions of these things. So you might ask, why is there even a lib? Why don't you just link against kernel32.dll? The answer is, I have no idea. I think it's stupid. The end. Okay, let's find someone who is programming. I don't see that here in the game development channel. Let's look in programming. I mean, maybe I'm missing something because I'm tired, but someone's playing Diablo 3. Now with eye tracker. Okay, someone else with an eye tracker, we could do that. I don't know what he's doing. Ray tracing. We could do some ray tracing. I'm kind of feeling the ray tracing so far. Or the weird Mr. Spock. Let's take a look. It's a fragment shader in Roblox? Oh, whatever. He's programming. We'll host it. See y'all later.